I'm Fuzheng Zhang, associate researcher from Microsoft Research. Today is my great honor to present our work, Collaborative Knowledge Base Embedding for Recommender Systems. This work is in collaboration with Nicholas Jinyuan, Defunian Xinxian, and Wei Ma. So let's begin. At the beginning, I will review the basic two types of recommendation methods. The first one is collaborative filtering. The core of this method is to tell me what's popular among my peers. Another method is content-based method. This method will use such as user profiles or item content as features to learn and supervise the model. The basic of this method is show me more of the same what I have liked in the previously. As we know, both types of methods has its limitations. The limitation is that for collaborative filtering, the limitation is that it only considers the interaction between users and items, and it totally ignores the items information. So there has cold start problems for new users of new items. For the content-based methods, the limitation is that it will recommend users the items very similar to the previous items they have liked before, so it lacks of diversity. Given collaborative filtering and content-based have its both strengths and limitations, hybrid systems is then proposed to take advantage of both sides. Here we just list several examples. For example, collaborative topical regression will combine collaborative filtering and topical model for recommendation. Another example is collaborative deep learning. This model steps further to combine deep learning for document understanding and then combine with collaborative filtering. Another method is the factorization machine. This is a very popular tool in recommendation systems proposed by Stephen Rundle. This model will fit factorization models with some raw features and usually can achieve good performance. In a word, these hybrid methods is very good for data sparsity and cold start problems, but they also have their limitations because the content feature they depend on is either only raw features or depend on single domain. Actually, except for raw features or only text, we need a more semantic representation of items. In recent years, as we know, there are more and more information on the web. So knowledge bases are built to represent the heterogeneous information on the web. Take Microsoft Sartorial knowledge base, for example. We can see there are many rich, structured, and unstructured information. For each entity, it contains many attributes and some text description and image description. And Sartorial also contains dozens of domains such as sports, entertainment, restaurant, movie, book, and so on. Actually, the heterogeneous in the knowledge base can be helpful to some application scenarios which are very difficult by the data from a single domain, such as Microsoft Bing's entity pen experience and Cortana experience. So in our work, we must answer this question. This heterogeneous information on the knowledge base can be helpful to boost the recommender systems. Actually, in our work, there are two types of data. The first is user implicit feedback. In the implicit feedback, if the user has some actions on the items, the value will be 1. Otherwise, the value will be 0. And then in the knowledge base, we have 3 types of knowledge. It is structural knowledge, textual knowledge, and visual knowledge respectively. First, for the structural knowledge, it is a heterogeneous graph. It contains movies and attributes as its nodes, and the relationships as its edges. For each entity, we also have its textual description and image description as its textual knowledge and visual knowledge. For example, for a book entity, its textual knowledge is the introduction and its visual knowledge is the front page. For a movie entity, its textual knowledge is the plot description and the visual knowledge should be the poster image. This is our framework. First, give the user item implicit feedback. We will map each item to the knowledge base. It will have 3 types of content knowledge. And then for each kind of knowledge, we will map it to a representation vector. For example, for the structured knowledge, it will embedding it to a structured vector. For textual knowledge, the textual embedding component will map the textual knowledge to a textual vector and similar to the visual vector. And then there is another item vector which is similar to the traditional collaborative filtering, and we will combine these 4 vectors to a final item vector. For the user vector and the final vector, they will be combined for a traditional, such as pairwise ranking-based collaborative filtering task. So first, let's have a look at how structured embedding is applied to structured knowledge. As we know, structured knowledge is a heterogeneous, undirected graph. It has nodes and edges. The nodes we know that the item entities and their attributes, and the edges are the different types of relationships between them. This heterogeneous graph, it is very huge, heterogeneous, and very sparse. So how can we learn a semantic representation for the item in this knowledge graph? For this task, we refer to a network embedding, which is widely used in traditional knowledge graph embedding research area. So this is this component. In this heterogeneous graph, we use the TransR, which is a kind of network embedding method for the embedding this heterogeneous graph. Given a trip, which is observed 2 nodes and an edge in this graph, for each node, we will have a vector representation, and for each type of edge, we will also have a vector representation. Actually, this graph is heterogeneous. So this model assumes that the vector space and this edge space, they are in different semantic space. So there is a projection matrix that will project each node vector to the space of the edge vector. And then, given these vectors, for each trip in this knowledge graph, it will be a score. This score means that if a trip has been observed in this knowledge graph, the score should be, this is some kind confidence of this observation. This should be high. For an unobserved trip, the score should be no. Okay, next, this is the embedding component for textual knowledge. Recently, such deep learning has been proved to be effective in document understanding, so we apply a kind of unsupervised deep learning method. This is called static denoising auto-encoder for the knowledge embedding. As this figure shows, this is an example of our model structure for our method. We can say the input is the textual knowledge with some noise, and the output is the clean textual, and the previous half part is the encoder part, and the following half part is the decoder part. We can say in the middle layer of this network, it can be regarded as the textual embedding of our component. Next is the embedding component for visual knowledge. It is quite similar to our textual embedding component. The difference is that For images, we know that convolutional network is usually effective. So we replace the static denoise auto-encoder for these fully connected layers. We will replace with convolutional layers. And similarly, the middle layer in this convolutional network will be regarded as the visual embedding vector for this visual knowledge. Okay, until now, in the knowledge base, we have 3 representation vectors for this item, and we also have another item offset vector. This is similar to traditional item latent vector in a single collaborative filtering. And finally, the final item vector, latent vector, will be represented as the sum of all these 4 vectors. And also, given the user latent vector, and we can make some pairwise ranking-based optimized function to solve these recommendation problems. Okay, we have conducted some experiments to evaluate our methods. Actually, we use 2 datasets. The first is movie length data. For this dataset, since we only use some movies which the user is interested, so we only keep movies with rating 5, and only keep users with at least 3 movies. Another data is called intent books. This is we collected from the search logs from Microsoft's search engine Bing. And this logs is from a 6-month query cleaning logs. First, we apply entity linking to find out book entity from these logs. To evaluate this entity linking method, we randomly select 200 extracted entities, and we found that the preceding results is more than 19%. And we think this result is good enough for later experiments. And also, we only keep users with more than 5 books. For both 2 datasets, we use Microsoft's knowledge base Satori. And for movie length dataset, since these movies have not been mapped to the knowledge base, so we first apply a 2-stage movie entity mapping method for the movie entity mapping. And this includes using features such as titles and these movies attributes. And next, to evaluate this mapping method, we randomly select also 200 pairs, and we find that nearly 92 of these pairs are correctly matched. And we also found that there are 134 movies that are mismatched. They can't be mapped to any entities in this knowledge base. And to build the structural knowledge for this movie length dataset, we also use the one-step subgraph, such as the category of this movie, the director, the writer, the actors, and so on. And for the second dataset, the intent books, since these book entities are already the entities in this knowledge graph, so we didn't need any matching algorithms. To build its structural knowledge, we use the one-step. We also use the one-step subgraph, including the book's category, author, published date, and so on. And we can see in the table there's some statistics of our datasets. For movie length, there is about 6,000 books and almost 3,000 items. And in our intent books, there is almost 19,000 users and nearly 20,000 books. First, we will evaluate the performance for each embedding component. First, we will have the study of the structural knowledge usage. Okay. There are some baselines, such as the basic collaborative filtering and PageRank with queries, and some others, personality anti-recommendation with the metapath, and filtration machine, and the heterogeneous of edges which ignores. Okay, we can see that our method uses the heterogeneous of embedding the network. It will achieve the best performance. And this is a study for textual knowledge. We also compare some baselines such as CMF, which will factorize user item matrix and item word matrix at the same time, and factorization method, which use backwards and raw features. And we can see also our model use the unsupervised deep learning model. We also achieve, at most time, it will achieve the best performance. And also, this is the results for visual knowledge. It is quite similar that our model have a better performance. Finally, we evaluate our whole framework, and we also compare with the methods such as only use two kinds of the knowledge, and factorization machine, which only use the raw features. Okay, we can see that our final framework achieves the best performance in both two data sets. Okay, finally, I will give the summary of our work. First, we narrate heterogeneous information, including the structure, text, and images from the knowledge base for recommendation. And second, we applied embedding methods, including graph embedding and unsupervised deep learning to extract some semantic representations. And finally, we integrate knowledge base embedding with collaborative filtering. Our framework can capture item representation and user-item interactions at the same time. So this is our work. Thanks for your attention. Any questions?
So can you dwell a bit on what you believe are the contributing features to the overall quality of the outputs? So what is it that contributes most? The collaborative part or the features you extract from the knowledge base?
I think the most contribution of this work is leverage the knowledge base for recommendation. It contains the heterogeneous representation of these items.
So I see when you deal with the data, you only keep the books, the users who has at least 5 books. And to my opinion, there'll be drop a lot of users.
Yeah.
Is there any way you can deal with those, inactive users?
Yes, we think that, thanks for suggesting this is a very good question. In our current experiments, we actually have not tested the performance on this very sparse situation. We think we can do some future experiments on this part. If we keep more users with very few items, how the performance will be some like. Currently, we also we only focus on these users with some kind of items, not with very few items.
I see.
Yeah.
Yes, hello. Do you have any intuition why the visual features help with this task? Because it's kind of literally judging by the book by its cover.
Yeah, actually, we list each performance of this knowledge separately. But if we compare these fingers together, we can see that actually the structural knowledge contributes the most, because there are many attributes of description these items.
Can you talk a little more about the collaborative topical regression? I want to learn a little more. I know that.
Okay. So in collaborative topical regression, we can see that this is the graph structure of this model, and there is a node which represents the user, and there is a node which represents the item. We can see the item is also linked to the topical model. For example, for each item, there is a document related to this item, and this document where it is composed of some words, and these words they are sampled from some topical distribution, and so these items it is on one side will link to the item representation, and on the other side it is linked to some word distribution. So it is a combination of these two parts.
We have time for at least one more question. There are. Okay, in that case, I have one, which is how do you, I mean, how scalable is this, the solution? Like, how long does it take to, run, and like, how big are your data sets in terms of size, and how would it scale?
Okay, that's a very good question. Actually, this is currently the main weakness of our method, because this method currently runs very slow for even a small data set. There are many structured knowledge, there are many nodes and edges in the knowledge graph. So it will only run on such as tens of thousands of users and items. Currently, it can run a more large data set because it will run even days and weeks. Yeah.
Okay. Thank you. Let's thank our speaker.
Okay, thank you.